Hello again. So in this video, we're going to be talking about the temperature and relative humidity sensing, which is in this little module as part of the environmental sensor development kit that we've been making as part of Design Spark. Now, the first thing you're probably noticing is that there's actually two sensors here, and this is because there's also a VOC sensor in here as well, but we're going to talk about that in the next video. But for now, the reason I start off the first video with temperature and RH is this is pretty much the cornerstone of all of your environmental sensing pollution data. Even if you are working, for example, on this particulate sensor, which we'll get onto later as well, it still needs calibration of its data in reference to a good, accurate local reading of the temperature and the relative humidity. So first thing to note, and I should point out that I'm not an electronic engineer, but we've been working with the wonderful AB Open, who have done all the clever code and PCB design of this. But as someone who's a product design engineer, I thought I'd explain some of the things I learned along the way so that they can help you with your project as well. So the first is recognizing that this little temperature sensor, and you can tell it here if I move it around, you'll see there's actually a hole in it. And what that is a little slot here cut around it. And it kind of makes sense when you think about it. It seems obvious, doesn't it, in hindsight? But essentially, you've got a temperature sensor that doesn't want to be next to any hot stuff, i.e. processors and LEDs on the PCB, the printed circuit board. And so you want to keep this thermally isolated by cutting out this little chase around it. So it has as much air around it because you're ultimately interested in monitoring the environmental temperature and humidity, hence the air around it. And so that is why we've actually done that. Now, the keen item among you might think, hang on a minute, the second hole is up there, the second sensor is also right next to it. That was something that we realized actually later in the design that just made sense. But by that point, everyone was so familiar with this, and of course it having two, it would have been a bit confusing if we just removed one, and then it looks very similar to the CO2 sensor. So a little bit of smoke and mirrors there, hope you'll forgive. But the design consideration was still perfectly rationalized, and we've got really good readings from putting the two sensors next to each other. Now, the sensor itself, as you can see, is absolutely minuscule, and this is one of them on a little breakout board. And I'll give you a little close-up shot of this now that I filmed. And that thing is truly tiny at basically about 2 millimeters square. And when you look at the technical data sheets, and I should point out that we are not paid or sponsored by Sensorion, but these genuinely do look around for your own independent opinion on this, but extremely well regarded, good quality sensors at an honest price. So this is the fourth generation. That's what the 4X means of this sensor, and it's what had all sorts of improvements since last generation. It's more accurate, and so for example, the humidity is, the accuracy is 1.8% RH, which is relative humidity, over the full range of 0 to 100, and a pretty good response time of 4 seconds. Now, I should point out that you can actually get readings quicker than this, but it's saying 4 seconds they will be fully accurate. So, similarly, the temperature accuracy is 0.2, which is pretty good for most applications, certainly for this one, and a very wide range of temperatures there as well. So as mentioned, the thing I try to sort of be a little bit responsible for when sourcing components is also looking at how will the electronics team integrate it, and seeing things like a good, nice broad supply voltage range. You can appreciate most things like Raspberry Pi and Arduino. Things like 3.3 volts are definitely preferred, so this falls nicely in the range. The current is only 0.4 microamps, so pretty low. And the interface is I2C, which even if you don't know exactly what that means, it's essentially an extremely common and well-documented interface for connecting with electronic devices and sensors like these and addressing them. So again, package size is very small, and a whole load of other documentation, which is really helpful. So even though I'm not going to go through all the detailed stuff which AB Open took of how to integrate the sensors, it's all there and ready and waiting for you. However, if you look at the design guide, I think this is extremely helpful as part of your considerations. So as you probably saw with this, we've got the white part, and the blue part inside is almost like a dog collar. It sort of fits and nests around the sensor to try and isolate it from any internal disturbances of it getting a bit hot, but also making sure that it's definitely only reading the external temperature. And this was basically referenced with the best of intentions from the recommendations from Sensorion here on their data sheets. And it gives some further explanation of why this is a good idea, and also some advice on sort of how far to keep things away from it. Other examples, as shown here, also just saying avoid things like direct sunlight, and that's why it has this unusual little design of it shielding from direct line of sight and hence direct rays of sun as well. So that's part of the little quirky configuration of those things as well. We're actually not trying to sort of monitor air flowing over the sensor, but if you were wanting to do that, there's also some good advice on the design considerations to do that in the best possible way. Having actually designed a humidifier myself whilst working at Dyson with another amazing engineer, basically I think this is a really, really good primer in its first few paragraphs, but then soon it does get into extremely complex stuff and all the equations. But I think I'd point out, if you were going to sort of, as it were, skip to the end, one of the most useful things here to Google is something called Humidex. And what that is, it explains the relationship between temperature and relative humidity. And the way you'll kind of relate to this on an everyday level is that if you've ever been to somewhere that is hot, say 30 degrees, but also tropical and has a lot of humidity, you'll find it's actually quite uncomfortable, and you don't, even though you're sweating lots, it doesn't really seem to cool you down. And that's because the air surrounding your body is so saturated with moisture already, it doesn't really allow much of that sweat to evaporate and hence cool you down. Conversely, if you're in exactly the same temperature, let's say 30 degrees again, but you're in a dry environment, that moisture can basically, through the difference, basically evaporate very, very easily, and so it cools you down considerably better. So this is what you sometimes see in sort of weather data, is they'll use a phrase which says feels like, and that's taking into account not just things like the humidex, but also wind. As you can appreciate, having a fan cools you down quicker as well. So even though this is some pretty hardcore science, I think it's worth having a little bit of a skim read and getting familiar with things like wet and dry bulb temperature, even if you don't get into the equations on first round. It'll definitely make your product much more accurate and give you a better understanding of what it is that you're trying to do with humidity and temperature if you are creating a product which is about sort of human comfort and environmental conditions. However, getting back to this closing point is that most things like particulate sensors, or indeed the CO2 sensor, which we'll get onto later, these actually need temperature and humidity benchmarking data to make sure that the readings are adjusted to be optimal and more accurate. So I recommend that whatever you're designing to do with air quality, you will need to take into account the temperature and humidity, almost certainly. So the next one we'll take a look at is VOCs.